we will have one talk, two talks for 1 hour, and a break in between. In the second part, Ramesh will tell us a little bit on his work on processes and AI. But before that, we will have a talk by the JADS people. It will be Willem-Jan and Indika, and they share the whole presentation, and starting with Willem-Jan. So please go.
Thank you, Bernhard. We'll have an hour to share with you our works that we are conducting within our research team at JADS. And in fact, this is done mainly by the PhD students and master thesis students. So what we'll do today is first I will give you a brief introduction of our view of data mesh data products. I know that this morning we have had an excellent presentation, in fact, early on, with a very nice definition. So you will see another one. And I will very quickly go over, I guess, the first introductory slides, after which it will be Indika presenting the real meat, I guess, of the presentation. But I will say a little bit more about it later on. So LLMs and data products both are a hype. They're fascinating topics. Nevertheless, at first I was a little bit skeptical myself about the potential of both the data products and the large language models. But nevertheless, I started experimenting a little bit with them in our team, and I think indeed that you will also figure out there is some potential indeed of using these types of generative AI tools within, I guess, software engineering and data engineering exercises. So indeed, data products are hot and happening. You can find many claims about the potential of data products, for example, and data mesh in news articles, in magazines, in blogs, everywhere on the internet, right? And I simply picked up one of data science leads of LinkedIn who claims that data products indeed, they will foster scalability. Having said data products, data mesh, they are very hot also in the Dutch, the Netherlands region. We are very active in the Brainport region that some of you might know. And we are working together with companies like NXP and ASML and some other big, I guess, semiconductor machine vendors and manufacturers who are experimenting with this alongside companies like ING, like KPN, and other companies where our graduates typically work. And most of the works that we will present later on, they are tried out to some extent in some of these companies. So yes, it's a lot happening, and yes, indeed, this was also claimed this morning. What is happening is that many of the data science projects, and I'm focusing here at data science because I'm working for this data science institute, so it goes beyond, in fact, let's say data science exercises, also AI exercises, and enterprise application engineering. But nevertheless, what typically happens right now is that a lot of the organizations, at least we work with, they bought in some type of data lake platform, and they started to centrally collect the data, stream it in a raw format in these data lakes, and then define a data science project. For example, they have a better notion of consumer sales, they have a better notion of customer segments. And each time you want to have more insights, you add another pipeline. So you develop pipeline after pipeline after pipeline, resulting in a data pipeline mesh, so if you will, a spaghetti, to use this word. Just like we have code spaghettis, now we have a pipeline spaghetti, which is pretty hard to manage, right? And in fact, what is happening, that some numbers claim that a lot of these projects fail. So a lot of projects that embrace this very centralistic approach with pipeline after pipeline, they fail. And this has a couple of reasons, which were also highlighted this morning. For example, one of the reasons is that the data doesn't reside, it doesn't stay where it belongs. And it belongs at the people who either, let's say, get or create this data. So it should not belong to IT departments within companies, but rather it should remain at the real owners of this data. And they should idealistically also be the ones who manage this data. So this is very much in the data mesh philosophy. And it reminded me myself a little bit back on the notion of federated database that some of you might still remember. So in fact, this notion of data mesh, it very much reminds me of federated databases, which we were developing in the mid-90s, right? And with which we have had also some experiences. But now, when we first saw this movement back to a central data lake, we now see this move back into more federated architectures. Having said data mesh, and that makes it also maybe a little bit different from the federated databases. It's not something which only belongs to the IT department. It's really a philosophy. It's really what you try to do is a cultural change. So which makes it even harder, right? So it's quite a big challenge to get this really implemented. So having said what we are moving toward is the data mesh approach. Where we have a cultural shift and an alignment between the operational plane, and this is very much the terminology that ThoughtWorks is embracing. And the operational plane, in fact, that collects all operational business data, which is generated through, I guess, your operational ERP systems, for example, manufacturing systems, med systems, you name it, right? And next to the operational plane, you have a different type of developers within your team that focuses more at the analytical plane. I mean, the analytical plane, these are the people in your team, the data scientists, that want to analyze data, that want to create new insights, that want to do predictions, that want to do prescriptive type of analytics, right? But where the operational plane is typically more the classical data, let's say, with software engineers, in the analytical plane, typically what happens is you have the data scientist there in a more, I guess, dominant position. And what typically happened indeed in the data lake type of philosophies, you would have the data lake developers, and you would have then for each data pipeline, let's say challenge, you would develop a new data pipeline, right? Were governed and managed by two different type of, I guess, also people within the organization. What we're trying to establish with the data mesh is that we want to try to bring it all back together, not develop a data pipeline each time over and over again that extracts data from the data lake, but really ingrain it within the data product itself. So a data product is a fine-grained capsule, if you wish, that offers its functionalities through the APIs, and that has in itself the data pipelines connected to it. And that really makes it a different approach in comparison to the central approach just introduced to you. So the federated data thinking, it stems from, or it embraces a couple of principles, if you wish. It's about design thinking, domain thinking, product thinking. So instead of, I guess, starting with a requirements analysis, just in the broad, you typically start with a domain analysis, really with the people at, let's say, the shop floor, the people with the knowledge, with the expertise, and you design a solution for the typically wicked problems, which are very hard, I guess, to solve. I'm quickly jumping over it because most of the material was already discussed earlier on. One other way to represent, let's say, the data product approach is that at the lowest level you have digital noise. This is just all the data that you get from your company systems or from your IT devices, whatever. You try to enrich it into business data, and the next thing is you try to come up with data assets which are a little bit better developed and typically stored in some kind of a database system or sometimes even flat files. So you have this bewildering variety of let's say data types typically within the organization, and then you try to curate these data assets into more user-focused products, which have more meaning, let's say, to the end users and to the data owners that have all the domain experience and expertise. So the higher up in the pyramid, the more, I guess, value-adding one thinks this data becomes. So one of our PhD students, who is currently not here, Stefan Driesen, he was here, I think, last year or the year before. And he will do his PhD defense, in fact, pretty soon. Bernard also will be there in the committee. And he came up with a pretty nice model and a quite nice depiction of what a data product should entail. So a data product has a little bit of code, of course, but the emphasis is indeed on the data. So although these hexagons here are represented at the same size, typically the data makes up the biggest chunk of the data product, obviously, and connected to it is, let's say, the metadata, right, which is encapsulated in this data product. And there's a couple of properties, he believes and we believe, which are important in the definition of a data product. For example, it should be interoperable. So the idea of data products is they are composable. They can work together with other, let's say, data products, maybe using contracts, maybe using, let's say, gluing code. They also should be discoverable. Sounds like something very simple, but the truth of the matter is that if we come in organizations, typically the data is fully scattered and one is unaware, one has in fact this data. It should be addressable, it should be findable, you should know where it sits, where it lives, the URI should be known. It should be understandable, so it should be self-describing. So in fact many of you also have been working in component-based developments, so you might in fact see many of these aspects and services, microservices as well of course. You see many of the characteristics that were defined before. And that makes, in fact, microservice technology, and one of our papers indeed also claims this, a very good candidate to implement, I guess, the data products. It should be truthful and trustworthy. Yeah, trustworthiness is a tricky thing, in particular when these data products are being equipped, let's say, in itself with the data pipelines, which are based on all types of machine and deep learning types of algorithms. It's a very interesting research topic in its own right, but in general they should be trustworthy, explainable, transparent, consistent, robust. All these properties should be assigned to data products. And also they should be feedback driven. So for example, one of the things that Stefan has been looking at is at a way for the users, the consumers of a data product to give their opinion. Very much like clients can give an opinion about a product when they buy something at Amazon, you could have something very much similar for the data products. So the promise of large language models. So what's in it? So, and maybe I skip this one. What are the potential pros for using large language models in data products? And I think it was also mentioned before, if you look at AI in general, large language models more in particular, there's a huge potential, right, all along the life cycle of, let's say, analyzing, developing, deploying, composing, configuring, managing data product types of architectures, okay? So what we found, in fact, is, I think there's something wrong here with the number, but okay. So it would, for example, it has the potential to help you with improving your data understanding. So for example, what you can do is you can use a large language model of any kind, in theory, to study a data, let's say, source, and extract the data and or generate automatically sometimes metadata, and to summarize the data sources within your organization. Also, it allows you to do knowledge graph integration. So what you can do is you can easily inject things like ontologies in these large language models. There's the claim of increased efficiency and automation. So for example, what you can do, and Indika will give a short, I guess, example of it later on, you can use it for automated data analysis and reporting. And also you can use large language models to some extent, we believe, to streamline data workflows, right? Where you can compose various data products, in fact, in a workflow, in a process in itself. I think this was one of the questions. So where's the process? Where's the application code that was asked earlier on? So taking, we believe, it should be the composability of these data products along a workflow is one way to do that. So, and then there is also the promise of having competitive advantages. I have picked up one which I thought is interesting. So what you can do with large language models is you can use them also to do predictions. We're doing it ourselves for the Rotterdam Harbor. So the Rotterdam Harbor is facing with a lot of changes because currently it's a harbor that lives from, let's say, all kinds of chemical companies. It lives also from the import of all types of crude oil that it refines. This will not any longer be, I guess, relevant in the very near future, right? So this will completely change. And what they are looking at is they are looking at Horizon 2 and Horizon 3 types of challenges, which will be relevant for them, not now, but within now and 5 years or 10 to 20 years. So they are looking at large language models, in fact, and they feed them with specific information to find weak signals. So one of these weak signals, for example, could be quantum. So can we use, I guess, quantum communication in Rotterdam Harbor to further improve the safety of communication between the harbor and vessels? Now that's not a weak signal, that's something they're already doing. But it's not a weak signal for them, but it might be for another harbor. Anyway, so they're using a large language model for that. And it gives them a real competitive edge, it is believed, at least by themselves. You can also address other specific challenges, and I've just listed a couple, ones in a quite arbitrary and incomplete way, so I'm not claiming this is complete, but one of the things we are interested in and also experimenting with is to, let's say, use large language models for your legacy systems and your legacy data, to get a little bit of understanding of systems which are 20, 30 years old. Contextual understanding, so what's the context of the data that lives in these databases, and compliance and risk management. That's another claim which is on the table. So a lot of claims, but what's really possible, and we started just to experiment with that. What are the risks of these large language models? Often forgotten. So when we went through the websites and through some articles, this is something one rather better not thinks about. So hallucination in general, of course it impedes the accuracy potentially of the usage of the large language models. Some of our students and PhD students as well, they are working in semiconductor companies, and they started to experiment with an American large language model like 1.5 years ago, but they were really stopped because of security reasons and the fear for leakage of IP. But also privacy, right? So privacy is another concern when you start collecting and feeding it into the large language model. And it's particularly true in the foundational model. It's not under your control. So how to deal with that? And also, in particular in these times, this constraint of sovereignty of the data is another thing which is in fact a risk of these large language models. This is why we're using all types of sandbox environments in our case. Bias and fairness. So again, this is something on the table. Transparency, explainability. So how did the large language model come to a certain design decision? It's completely opaque, it's completely unclear in many cases, hard to explain, and thus hard to manage, and unpredictable to a certain degree. And one thing managers don't like is unpredictability. Another thing is ethical constraints. So yes, this is an increase of productivity, and yes, then it is claimed that's good. So then you can really look at strategic type of problems. I don't think this is in general true. Last week I was talking at a congress for a lot of industry partners, and there was more or less general consensus, especially in these times. Large language models and the increase of productivity that goes with them is a perfect way to make the organization more efficient and to reduce the number of jobs. So if this happens in general in society, this could, in principle, have a huge impact on our jobs. Anyway, it's a different topic. We can talk about it maybe in the break or later tonight or one of the coming days. And of course, there's the threat of version drift of these large language models, which is uncontrollable for you, and the updates to the foundational model. Yeah. So there is a lot of ways, in short, in which large language models can be beneficial. And still there is the risks that we have to deal with, but in principle they can be beneficial. And as I said, we started to experiment with it along a couple of axes. There are fair data products, data product modeling and inspection, data product deployment, large language based data products, data product governance, a lot of data products, and observability, in fact, of these data products. And what we would like to do in the remainder of this presentation. Hopefully we'll have a little bit of interaction later on when you're ready with the emails and other stuff that you're doing right now. What we'll do now is we'll come up with the practical examples. And I want to give the floor now to Indika.
Thank you. So I'm going to present some of the work I did with my student, mostly master's student. Some of them are related to data product. All of them are using LLM. Some of them are related to microservice but applicable to the data product. First one was about making data product pair. Pair here means everyone probably know, findable, accessible, and interoperable and reusable. In general, to make something like, for example, data pair, we need metadata. Metadata means rich metadata that enable us to compare, for example, two data set or two data product and see whether they are similar or how they are different, and if there's some different, how to mitigate that difference and so on. And also, especially when we consider data product and data product offer data, these data usually need to be interpreted with the domain-specific knowledge, because same term may have different meaning in different contexts, and also a lot of communities, they have their own vocabulary. So we need rich metadata that describe different aspects of data product that enable us to use complex criteria to compare data product. And also, if we want to use, for example, computer program or automate for example, comparing the data product, searching for data product, then we need to represent metadata in the formal language, the language that used for the knowledge representation. For example, now if you consider these queries, for example, first query, let's say that the data consumer want to look for data product and offer data that can be used to build a GNN graph neural network for predicting credit card fraud, and also ideally with some performance result. In order to search for this kind of data, the information about, for example, schema is not good enough. We need more metadata. For example, there should be metadata indicating whether this data is graph oriented or not, whether what type of use cases for which this data can be used, also previous usage of this data by different maybe other data consumers and so on, all the history of data usage. All of these information is necessary to make the decision and select the data product. For the second question again, if you want to replace one data product with another data product, one way to check the schema level compatibility syntax, but syntax not good enough. Sometimes the same syntax have different meanings, so we need to also consider semantic. Even the semantically or syntactically interoperable, still maybe data quality may be different. The regulation under which data should be used different and so on. So we need to have a lot of more information in order to really see whether this data product can be replaced by another data product and so on. So most of the information about the data product are available in different sources. So we should be able to extract the required metadata. So this is the one of the work we did, almost complete at the moment. So there are, for example, a lot of information sources that can provide metadata pro data product. For example, model card, data card. Then companies use, some of the company, even big company use wiki pages to describe the data product and so on, natural language, and also history of data usage, tutorial how to use the data product and so on, a lot of other things. And also the user reviews. Most of them are either textual or can be multimodal. But if you want to use some automated way to compare this data product, then we need to use a formal language. Very common approach used by the pair committees, ontologies. So in that, because of that, we also use the ontology. So here, LLM can be used to extract the metadata, in this case, triple that populate the ontologies from these different type of sources. Then regarding the ontologies, because data product itself can take some data, produce some data, maybe take some module, produce model, produce some data and so on. So it has a lot of different artifacts. So we need to have different type of ontology that can describe all of these artifacts. In fact, there are a lot of ontology. For example, there are ontology we can use to describe the model card. There are ontology that we can be used to describe the data set used for data mining and so on. Here we use few ontologies. Then once extracted triples are stored in a graph database that support the ontological reasoning. Then let's say that user want to check the, in this case, let's say user want to see if the product A and B are compatible. In order to do that, we need to, with ontologies, we need to generate the Sparkle query that can query the graph database and do the semantic matchmaking. But again, the user cannot really write these queries. Again, here large language model can help by translating natural language query into the Sparkle query. This is to support the search interface, so this is to support for the search for the different data product. Another option, I'm not sure that how much you're familiar with the graph rank. Another option to use a graph rank. So in this study, we compare these options, so see two options and whether what actually has the most benefit and what are the pros and cons. And also we compare how effective each of these two tasks. We use the data card and model card only in this case. The results are satisfactory, but I don't have numbers yet. It's almost finished work, but we still need to do some work. Then regarding data product inception or come up with data product or creating even the model for the data product, this process usually need collaborative effort. Even in the organization, if you're going to develop a dashboard or even if you're going to do a data pipeline, always you need to interact with the domain expert. Because you, as a data engineer, they don't have a domain expertise. They cannot accurately interpret the data and so on. This collaborative process in a company usually done through interviews and so on, which is, if we do in physically, it's time consuming. This potentially can be overcome with multi-agent system where role-playing agent, that agent simulate these human roles, then also interact as human interact, and then in the end produce the, for example, data product model we need. We did not did the work on the data product domain, but we did a similar study for the business process model discovery, which is comparable. In the business process discovery, typically again need to, let's say that there's a company have a business. In order to document and create a model for this business, typically in this case actually we did this study with the process consulting company. The consultant company interview the people in the business and then the knowledge gathered from those information create the model. These are the typical role. So in the business domain, there are process workers that implement or support the business task. Then the company can have different role, like for example, someone to do the interview, someone to do the modeling, someone to manage everything and so on. What we did in this study, we use multi-agent system to simulate these roles, all of these roles. We compare different setting of multi-agent system. This is actually one of setting, in this case team, where there are different agents, each playing single role, but also there are alternative, like for example, we can have a one agent replacing playing multiple roles and so on. In collaboration, they conduct the end-to-end process, doing the interviews to then the synchronized information and creating the final process model. We evaluated this with 3 LLM and 3 different multi-agent system pattern and also 3 process model from the literature. This result probably cannot see, but these are 3 use cases. In general, results are good, but also when the number of agents are increasing, then some of the model, because due to their robustness issues, because model have a lot of failures, the performance drop. But what we concluded is that we can actually use this simulation to replace the human domain expert. We did a lot of other analysis, for example, resource usage like token consumption, error, and so on. This is all performance. Then regarding data product development, data product has code to do the data ingestion, transform, validate, restore, and offer the data. As well as we need policy to make sure that we regulate the access to the data. Maybe we need test cases, also data quality testing code, and so on. LLM can help to generate, refactor, migrate this code. We did several studies. We did several studies on generating data quality tests, generating policies. Policy part I will later explain. Then also we did some work on generating data pipeline. One of the study was the action design research we did at this medical center. It's one of the large medical center in Netherlands. They have large data engineering team. They have to develop a lot of clinical data pipeline. In this case, ideally in the natural language, we should be able to provide the objective of the data pipeline. Then LLM should be able to translate this objective into the actual pipeline code, for example, Python code. In this context, the data engineers in this context, when they develop the pipeline, they follow three-step approach. First, they create a textual description of the pipeline. Then they use relational algebra to formally document the process, the pipeline, then implement the source code. So we have to see whether LLM can actually replace the automate complete process. So we did action design research. We developed artifact in several iterations. In the design science research, usually we are interested in come up with the design principle. Here we identify 13 design principles, and also part of the study we evaluated different LLM, different prompting strategy, and so on. In general, LLM were good about like this part, but in the code generation, some limitation. But in any case, the conclusion was that yeah, LLM can be used, but it should be used as a pair programmer. Then about the LLM based data product, here what I mean, use LLM to implement the logic. For example, instead of training a custom machine learning model, we can use LLM to make the prediction. And also LLM can do the data transformation, LLM can find the data quality issues, and so on. We did one study, tried to use LLM in the context of discrete data processing. Use case was credit card fraud detection. We were more interested in accuracy important, but also we wanted to see the real challenges of using LLM, like the energy efficiency, especially with the local LLM, and also fairness. This is related to the credit card fraud detection. This is the experiment setup. This is a realistic data streaming environment. This is the Kafka, the data ingestion, then data processing, which is the mostly speech engineering. Then there is a way to create custom prompt, because we want to try different type of prompt, also using different context. And then we run is prompt again LLM to do the inference, then measure the energy usage, and also fairness, and so on. What we observe here, in this study, we also compared a 10 open source LLM and also 2 commercial on energy usage only for the open source, because we cannot measure the energy usage of the commercial. Then also we compare them with the traditional model. What we observe, traditional model actually perform better, and also compare with energy usage, much better than the LLM, or LLM almost make impossible to use in this kind of context at the moment because of the energy usage. And also fairness issues are, both models have fairness issues. Then, this is related to data product, development. Then So once you have a data product, but still you need to deploy data product. Deploying data product can be again complex thing for us, even the data engineer. For example, consider data product that take data from some Kafka, do some processing in this part, then push the data to Kafka topic or storage bucket to, and also configure some access control policy so that only the people with right permission can access the data. This can be complex, and especially when you want to configure this kind of thing in a cloud environment. Potential approach to simplify this is to use infrastructure as a code. However, even if you use the infrastructure as a code, developing them are very hard because you need a lot of knowledge about the infrastructure as well as the language, infrastructure code language. Again, LLM can potentially help because LLM can maybe generate the infrastructure as a code from natural language. So we try to do that. In fact, there was one work from very good venue. It started to try to do that. In this case, they created a data benchmark to generate that Terraform that comply with the policies. Their baseline was very, accuracy is very low. And what we did, we tried to understand what goes wrong in their context. So we tried to analyze all the errors and so on. Then come up with the taxonomy of error when we use LLM to generate the infrastructure code. Based on the taxonomy, then we observe that some of or most of the error happen when LLM cannot figure out the dependency between module and so on. So we come up with solution to inject the configuration data. Configuration data is the data that describe the, for example, if you use Terraform, their dependency, their parameters, dependency between parameters, and so on. This configuration knowledge can be mined from the documentation as well as the GitHub repos. So we did that. Then we evaluated two approaches. One is to use the naive RAG approach, where you simply take this text data and provide as a context. Other one is to build the knowledge graph. We were more interested in the knowledge graph. Then this one actually significantly outperformed the baseline. So our approach, this is just one experiment. We did a lot of experiment regarding the context retrieval and their effectiveness. So at least this show that we can generate, we can use LLM to accurately generate infrastructure code that can be used to deploy any type of application. Then regarding data product governance, data product governance in the data mesh, they promote the computational federated governance, where the governance decision ideally should be automatically executed. One of the approach also suggested by Sharma to use policy as a code. With the policy as a code, similar to infrastructure as a code, we use programming language to define the policy, and then we can also use the software engineering practices to manage this policy and execute them and so on. Here shows simple example. One of the widely used open policy, policy as a code is the open policy agent. It's also widely used by even some of the big cloud providers. So let's say that we have a natural language expression of the policy, ensure that this storage volume are encrypted to make the data security. Then the policy as a code configuration, the file will be like this. Again, for the developer to create this file is difficult because you need to understand a lot of things. Once we have, let's say that there's a way to generate or create this file, then we can use this as part of the, for example, product deployment to see whether if there's a violation of the policy. At runtime also we can use this policy to control access to data and so on. In this example, this is related to infrastructure code. When we going to deploy the application, first do the policy check. If it is failed, then do not deploy. Also, once we have deployed, at runtime, it's possible someone do manually some changes to the infrastructure which violate the policy, which can be detected by monitoring the system, and then again check the policy violation and so on. So policy as a code combined with the monitoring and observability can help to ensure the data governance. The challenge again to create this policy manually. So we again tried LLM, whether LLM can help here to generate the policies. In this context, we were more interested in generating the least access control policy, which is the policy typically when you have a complex system like, for example, microservice architecture or set of data product. We need to make sure that only the data product or service that has privilege can access the data. If they can read, only can read. If they can, then they cannot write, and so on. In order to generate this policy, again, let's say that if the user want to generate the policy for a specific data product or microservice, in fact, this study we did in the context of microservice, then the developer should only be able to generate the policy should be by saying only, for example, say that generate the access control policy for this product, this service, or between these two products, and so on. Then we, in this case, we again use a graph rack where we provide the dependency between different, in this case example is the microservice actually, dependency between different microservices. Then the LLM can utilize this knowledge to generate the policy accurately. Here there's also a repair loop where we deploy the policy and also check if there's error, then put the error back to the LLM agent, then do the repair. But overall, again, this was again achieve very high accuracy after all this step. We also experiment with several LLM as well as several applications. Finally, about data product observability, we did some work again in this context. This is in fact one of the architecture we propose in one of our paper. So they are data product. They are interaction governed by the data contract that define the terms as well as obligation of different data producers and consumers. Here, in order to see whether there's a contract violation, we need to monitor the data product. In order to do that, we need to instrument the data product. Instrumentation should generate the metrics, logs, also any other data that help to understand if there's a violation of the contract condition or terms. If that is the case, then there should be a way to remediate that. In this context, LLM also can be used for several purposes. For example, we can be, let's say that we have a data product, but then in order to correctly instrument that data product to support specific data contract violation detection, that part maybe LLM can automatically do that. For example, automatically creating the correct data quality test and so on. And also contract can be maybe need to be defined as a natural language. Then then we can probably generate the enforcement code like policy as a code, data quality test, and so on based on the natural language. In fact, I have one student working on that. Then also another key issue is when you have the contract violation, then the human need to be able to understand that. Then we need to provide human understandable explanation. Then also need to be able to do the root cause analysis and so on. Most of them can be done with the help of LLM. In fact, we did one study regarding data quality automation. In this case, automate the data quality assessment. This is a study, ongoing study with design science study with the data engineering consultant company. With some interview with the company people, we identify set of requirement, then also come up with set of design principle. This requirement mostly related to the automation of the data quality issues and the fact that data quality issues, interpretation of the data quality issues as well as understanding their root causes need domain knowledge. Then there should be way to use domain knowledge to check for the data quality issues and so on, and interpret the data quality issues and as well as data quality rules. Then also the human, most of the domain experts do not understand the technical level data quality things. They need something that they can understand, so we need to be able to convert technical data quality issues into the business level quality issues. For that, this is the current artifact, which we have already developed, but the project is ongoing. This is the first artifact. We use here generative AI in 4 places. One is to partially generate the domain knowledge. Domain knowledge also can come from domain expert as well as documentation and so on. This is to mine the domain knowledge from the existing dataset. Then there's the LLM agent that interprets this domain knowledge to identify the domain rule, which can be mapped to the data quality check, as well as some other high-level goal which cannot be directly mapped to the specific data quality check, but need compressed implementation to assess them. To do that, again, we have some the LLM that can generate the code to do this part. In the end, once we have all this data quality check, we can check the data quality issues. Once we have discovered the issues, then we need to be able to do at least 2 things. One is to explain if there's a data quality issues, what was the root cause, and also provide the explanation that the human can understand. This artifact is successful. We are actually doing with data engineering consultant company. They have customers, so we use their data and also interact with them. These are the things we have done so far at the context of data product, data pipeline, and so on.
You done?
Yes.
Yes. Thank you. So we are open for questions. Arif, yeah?
Thank you very much. Very interesting talk with tons of different.
Speak loud, otherwise those people don't. Or take the mic.
Perfect, thank you. Yeah, thanks a lot for the great talk. Tons of interesting topics and applications. My question is about the agent-aided creation of data products. I think that when we try to get away from this kind of data mess, right, that we have before data mesh, one of the main issues is often a lack of ownership and clear responsibility structure, right? That we have data where no one feels responsible for. Now, I think that the approach with letting agents help with the creation and even coming up with interviews, etc., is really promising. But I'm wondering, do you see the risk that if you let agents and AI in general help too much with the creation of data products, that this could again result in a lack of ownership, so that people basically just let the AI create data products and then they think like, well, the AI created the data product, so I'm not responsible?
Yeah, true. I believe yes, because let's say, LLM even that example is here we use LLM. LLM in fact can make even incorrect decision. Then who is going to take the responsibility? I think that problem is there with LLM. I mean, when you use at the company LLM, not just for data or anything, someone need to take the responsibility. I believe, use LLM to create a data product, then there should be still some owner for that. Take the responsibility. If there's something wrong with the data product, he's the one going to somehow be responsible.
Thank you.
Okay.
Because in fact there are a lot of issues and they can hallucinate, some fairness issues, a lot of issues here.
Maybe as an add-on, indeed we have some experience with it, also in the context of European projects. So you always need to have someone in the loop, maybe off the loop, but outside it's not on.
Thank you. So there is another question.
Thanks for the talk. You had on one slide, you didn't say much about it, but on one slide you had you had a series of topics, and one topic was using LLM to generate data transformations. Yes, that was the slide, transform. I was wondering if you could comment on the data transformation topic. Did you have LLMs generate SQL code to transform between different data formats, or how was that?
Yeah, actually, this one did not generate SQL code. This is the Python Panda code. There are, yes, actual code, the Python code, but there was actually another project that did not describe that do the text to SQL, even the text generated as SQL.
So the mode was natural language to SQL.
Yeah, natural language. Yeah.
Okay.
There's another project, something become bigger.
Are you aware of any work? I'm just asking because I'm interested in the problem that you might want to try to generate data transformations not from natural language but from different data sets. So you imagine you have different data sets and how we want to somehow help with discovering that the same information is being represented in different ways in those different data sets, and then automatically generate some code to mediate between these different representations.
Yeah, I think I didn't do that. I believe it's something I wanted to combine, like, let's say that somehow we extract the metadata, then we know that there's a difference between the data product. Possibly that whatever we extracted can be used to maybe augment and then generate. So, yeah, first do the semantic matchmaking, then we identify, let's say, these are the difference between data product, data set or something. That whatever output maybe then can be put to the data generation agent. But I didn't try, but that's something I wanted to do actually.
What was your experience positive specifically with the data transformation?
Yes, in this case, let's say this was actually done several months ago. Using GPT 3.5 or 4, I cannot recall. There were two actually, Copilot. This part was really good. Then the actual code generation, there was some issue, but issue in the sense we have to resolve them with providing different context and can be improved, but it's not necessarily perfect.
Okay.
But this part was really good. It's a relational algebra.
Okay, cool. Oh, yeah. Okay, cool. Thanks.
Okay. Next question. Yeah. Simon.
Yeah, thanks for the interesting talk. A question regarding the policy as code. Perhaps you can go to the slide. And then one. Then the next one, where they showed the policy. No, with the code.
Sorry.
That way.
This one?
Yes. So maybe my question is, so what we are doing here, use LLMs basically to generate those files. So yeah, that I think that works fine. My question is, can we just use LLM instead, all the way? So what is your thinking? So could we skip this formal language and could we say, let's let the LLM just do it directly? Why do we need that?
Need to try. I didn't try, but in order to do that, of course, in addition to this thing, they need to provide all the data as context, some rule to make the decision. Maybe I didn't try. Maybe possible. Yeah, it's definitely possible, but I didn't try. Should be possible, but possible in the sense maybe not work 100% accurately. Then there will be a lot of issues because LLM take a lot of energy and so on. But I didn't try. It should work maybe at least to some extent.
Thanks.
Further questions? Well, let me just ask you maybe a last question. It looks to me that we are all too lazy to do our work. We just ask LLM to generate something. How can we trust that all the things we want to have in the final result are actually there in the right manner?
Yeah, then let's say that then for that, one thing maybe. So what we probably can do, I cannot provide the answer because it's an open issue. In this case, for example, there is original benchmark, then we use it, then we actually did manual analysis to understand the type of errors. These are the type of errors. Then we can, let's say, have some code to classify these errors. Then we can use the same taxonomy then to always compare whether the generated thing have these errors or not. Maybe I saw some other papers that use the ontology with some fact to do some kind of to reduce the hallucination and so on. There are some work doing different things. But answer is I can provide direct answer for that.
Yeah, that was a nasty question.
Yeah.
Yeah. Okay, thank you. So let's close the first part of this session, have 15 minutes coffee break, and then we resume, and Ramesh will tell us about agency AI. Thank you.